All right, good morning, everyone. How's everyone feeling? Nice full night last night. First, you got to start the night off with a midterm, and then you got to see the election. Was everyone up watching it? Pretty much? No? Some yes, some no. I was up to like 11 or 11:30, and I'm glad I went to bed because, yeah, it's not decided now, and who knows how long that's going to take. Midterms, I don't have much to say about those yet because I haven't looked at the written part, although I can say that the Acorn part looked pretty good. The average on that part was like 75 or something like that, which is pretty good for a course. Lots of high grades too, just happy to see. So far so good with that. I checked everybody's upload as well. I didn't look at the answers. I just checked to see that I could tell it was there and there's the right number of pages and that sort of thing. And so if you haven't heard from me, you're good. So if you're worried about whether your upload actually worked or not, I think everybody in this whole section is fine. What else? Nothing else. We're doing chapter 6. So what I want to do at the beginning of class today is just recap what we learned so far in chapter 6. And we learned our first two reaction mechanisms. Both mechanisms are for substitution. And we said there was two different types. There was SN1 and SN2. What does the S stand for? Give me an S. What's the S stand for? Substitution. And the N? Nucleophilic. And the 2. What does the 2 mean for SN2? Bimolecular. Good. Rate determining step is bimolecular. SN1. Rate determining step is unimolecular. One molecule is involved. So SN2 looks like this. SN2 would be if you have, I'm going to use the example of a primary alkyl halide, like this. Why is it primary? Because the carbon that has the bromine, which is the leaving group, which is this one, is attached to only one other carbon. Sometimes we call these carbons the alpha carbon and the beta carbon. Right? Alpha is the one that the leaving group is attached to. Beta is anything that's attached to that. So we could say that if it has one beta carbon, it is going to be a primary. Primary alkyl halide. Great. Let's get a nucleophile. What kind of nucleophile do you want to see today? How about, well, we could use bromide again. That's not going to do much interesting, but we need something either neutral or something negatively charged, but it needs to have a lone pair. So why don't we pick something like HS minus. This is a great nucleophile. Okay, it's got lone pairs, negative charge. It likes positive charge. And because the bromine is a little bit electronegative, we might say that alpha carbon is slightly positive and the bromine is slightly negative. And so that HS minus is looking around for negative charge and it sees one, looking around for positive charge and it sees one on the carbon-bromine bond. So what it'll do is it'll come in and it'll attack like that, knocking the bromine out. So one of the lone pairs on HS becomes a new SC bond, and the CBr bond breaks and the pair of electrons goes to the bromine. Are there any other bonds there that I didn't show on that alpha carbon? Yeah, 2 hydrogens, right? Let's draw them in. Hydrogen, hydrogen back there. So what happens is this reaction happens. I'm going to kind of draw it like this. What's this that I drew here? Is that a molecule that you could put in a bottle, take home? You can't do that with any of the chemicals in our labs, by the way, but hypothetically, this is not a real stable molecule, right? What would we call that? I'll give it a negative charge. This is just something along the way to making that product. So there, we're done. So if you have an potential energy diagram, your starting material is down here, goes up like that, and your products are over here. So what's this thing up here in the middle? So this thing that I drew, it's it's not an intermediate. Transition state. Transition state is like a highly strained, super unstable molecule. It's the high energy point of a chemical step, and it's a molecule where bonds are partly being formed and partly being broken all at the same time. That's what these dotted lines are supposed to represent, that is sort of like half a bond maybe. And the sulfur carbon bond is starting to form, the carbon bromine bond is starting to break. One forms as the other breaks, so they come in, one enters and one leaves all at the same time. And we give these sorts of things a symbol that looks like this, double dagger. That's going to be what we have at the top of our thing here. And single chemical step. This is a one-step reaction. This is SN2. And it's bimolecular because there is 2 molecules colliding in the rate determining step. Rate determining step is the only step in this reaction, so that's good. Cool. Everyone's happy? Now, we talked about what SN2, what made it fast and slow, and we said SN2 is fast if you have a methyl with a leaving group or a primary. But that as you go to secondary and tertiary, it starts to slow down. In fact, tertiary is so slow that it doesn't ever happen. And we said that's because if you look at a molecule like the backside of that molecule is so blocked that a nucleophile can't approach. Too much junk in the way. All right. So methyl and primary will do an SN2 reaction. The other choice was an SN1. We have a molecule like this. We said, this is tertiary because if we have our alpha, we have a beta, 3 beta carbons. And that means it's tertiary. That means it's 2 hindered is the word we often use, sterically hindered. There's not, the back side of that molecule is blocked up with methyl groups. The nucleophile can't get in, it can't see that alpha carbon, it can't attack, so you can't have SN2. But this goes by a different mechanism, it goes by SN1. And with SN1, what happens is the leaving group goes first, and what that gives you is a carbocation. And we could use the same nucleophile as before. And I'm going to remove that arrow because I don't want you to confuse it as a reaction arrow. Then what can happen is the HS minus can come in and attack. Like that. So this is 2 steps. First step is loss of the leaving group to make a carbocation. Second step is once the carbocation is formed, the nucleophile attacks. It's kind of the same as SN2, except SN2, the 2 things happen at the same time. For SN1, just the leaving group leaves first, and then the nucleophile attacks. This happens in 2 steps. The slow step here is always, in fact, any reaction you see in this course, The rate determining step, the slow step, is always going to be the step where a carbocation forms. Because a carbocation is a high energy thing. It's unstable. It doesn't have a full octet, 6 valence electrons only. And so for that reason, forming it is difficult and therefore slow. So the rate determining step, because this is the RDS, rate determining step, we call this unimolecular because only one molecule is participating in that first step. Only the substrate, only the alkyl bromide is reacting, breaks in half, loses the bromide, and yeah, first order. Unimolecular. We have good names for things in chem. Unimolecular means one molecule. Couldn't be clearer. Okay, so that's where we're at. Refreshing your mind that we have these two mechanisms, SN1 and SN2, that both do substitution. Okay. We want to look at how you can tell if a molecule is going to do SN1 or SN2. You have an alkyl bromide, you have a nucleophile. It's going to want to do substitution, but how can you tell? Well, we already talked last class about how SN2 will always be the option for a primary or a methyl alkyl halide. We also said that if it's tertiary, it will always be SN1. So the troublesome one there is the secondary, right? Secondary might look like this. If that's alpha and this is beta, we have 2 beta carbons. This is a secondary alkyl halide. This could go by SN1 or SN2 depending on the conditions. And this is maybe a big piece. There's a lot of nuance to what we're going to be doing going forward. And you can do things when you're doing a chemical reaction to sway it to go SN1 or sway it to go SN2. And that's what we want to be able to do. We want to know how to control, as you know, you can't get in there and tell the molecules what to do, but you can control the conditions. You can either use heat or not heat. You can pick the solvent. You can do all sorts of different things to try to sway the reaction to go one way or the other. It's a lot of what chemists try to do. And you know, we're going to look at the example of SN1 and SN2 and a few other ones as well. But the truth is that often chemists can write stuff down on paper and read journal articles and all that stuff and make an educated guess about what's going to happen in a reaction. And still very often you try it and something different happens. And that's why organic chemistry is very much an experimental science, which is too bad COVID is sort of taking the wind out of those sails right now. But the thing is, yeah, we can do all this stuff on paper. All of this chemistry that we're doing right now was discovered about 100 years ago in the 1920s. So it's pretty old, but there's, you know, think of chemistry as almost like, organic chemistry is almost like a tree growing roots, and the roots keep growing and branching and getting further and further out. We're very close to the trunk with what we're talking about right now. We're looking at those big fat roots that go all the way out, but they're still growing. The edges are still getting more complex, and we're still learning a lot about how reactions go and reaction mechanisms work. So, you know, the things that we're going to be looking at to distinguish between SN1 and SN2 aren't only helpful in terms of figuring out which of these two mechanisms is going to happen. It's a general principle. Like, you can control the solvent for any reaction and potentially switch what sort of products you get or how fast the reaction goes. So these ideas that we're going to be talking about are applicable to almost every single organic chemical reaction. First thing we talked about this last class, was concentration and identity of nucleophiles. We said that some nucleophiles were stronger than others. The strongest nucleophiles are ones that are negatively charged. That makes sense. So strong nucleophiles will favor SN2, and it has no effect on SN1. And that makes total sense if you think about it. SN2, the rate determining step, is a collision between a nucleophile and the alkyl halide. You make that nucleophile a better nucleophile, that step will be faster, And because it's the rate determining step, the whole reaction is faster. SN1, the rate determining step is you're waiting for the substrate to fall apart. You can make the nucleophile as strong or as weak as you want. It's not going to change the rate of that step. So you can't make an SN1 reaction faster by putting a hotter nucleophile in. You don't have any latitude there. So really all you can do for SN1, well, there's other things we can do we'll talk about, but stronger nucleophiles will favor SN2. So, if you have a secondary and you want more SN2, you should be thinking, can I use a stronger nucleophile to do this step? Solvent effects. Now, we have a whole variety of solvents that we can use in organic chemistry. One classification that you've probably already, you may be somewhat familiar with, is classifying something as polar or nonpolar. We did this a lot in chapter 1, deciding if a molecule will, the types of intermolecular forces. We had questions like this on the midterm last night, questions like that on the oral exam as well. And this is just the classic, look at the structure of the molecule, look at its shape, do dipoles cancel out, is this going to be a polar solvent? And we just call it a solvent if it happens to be a liquid. So take, for example, something like water. Is water a polar liquid? Yeah, water has a dipole, and therefore it will behave as a polar molecule, and it's a liquid, so those are the two things we need for this to be a polar solvent. Take something else, for example, cyclohexane. Cyclohexane is a liquid at room temperature. Or let's say CCl4, carbon tetrachloride, also a liquid at room temperature. These two things are nonpolar. They have only dispersion forces. They don't have any polar bonds. They don't have that. So we would classify these ones as a nonpolar solvent. Okay, so think of all solvents that we could pick. We can split them up into these two types, polar and nonpolar. We can further subdivide the polar ones as being either protic or aprotic. And this might be a new one for you today. So a protic solvent is basically one that has a hydrogen or a proton that can be removed or exchanged. So typically they're things with OH and NH. So anything that can hydrogen bond, any hydrogen bonding solvent is a protic solvent. And maybe a few other niche ones with like SH. But an example of a protic solvent would be like water. Any alcohol is a protic solvent. Any liquid carboxylic acid is a protic solvent because it has an OH. Any amine can hydrogen bond. It's a protic solvent as well. And those are probably the majority of the ones that you would come across. If you have a polar solvent that doesn't have a hydrogen bonding hydrogen, then we say it's aprotic. It's got no proton. It's got no proton that can come off and on easily. So what would be an example of an aprotic solvent? Something like this molecule. What molecule is that? Anyone recognize the name of that one? This one is acetone. Acetone, nail polish remover. It's a ketone, but it doesn't have any OHs or NHs. It can't hydrogen bond, or at least it can't be a hydrogen bond donor. It's got no hydrogen OH, NH. So this is a polar molecule. It's got a dipole, but it's aprotic. Other examples of polar aprotic solvents that are common, one looks just like acetone. It's this molecule, put in the lone pairs. This is called DMSO. Dimethyl sulfoxide is the name for this. This is one you may have never heard of before. But in organic chemistry, this is a fantastic solvent. It's very good at dissolving salts and organics. It's one of the best solvents out there for dissolving a wide variety of things. It's used a lot in biology because you can mix it with water, and it allows you to put into a tissue some compound that wouldn't otherwise dissolve in it, something that's not soluble in water. Other thing about DMSO is actually it'll travel through membranes. It makes membranes kind of permeable. I heard a story once about a man who tried to murder his friend. I guess not really friend, I guess, if you're trying to murder them. But and what he did is he took sodium cyanide and he dissolved it in DMSO and then kind of painted the DMSO on the back of the steering wheel. And every time he'd grab the steering wheel, what would happen is the DMSO would migrate through his membranes in his skin on his hand and pull the sodium cyanide through it, which would get into the bloodstream. So sodium cyanide was slowly building up in his blood, and eventually he got poisoned. He was killed. So yeah, don't try that. That's DMSO for you. We have a few other ones. These are sort of more exotic things. They're used all the time in organic chemistry, but yeah, you probably haven't heard of them before since you've never taken organic chemistry. This molecule is called DMF. This is called dimethyl formamide. So it's got a CH3, a CH3. What functional group is there in this molecule? Amide, right? No amine. It's got an amide. So dimethyl formamide. These are all solvents. Oh, another good one is acetonitrile. This is my favorite solvent of all time. It's CH3 with a carbon triple bond N. So yeah, this is called acetonitrile. Everything you want in a solvent, acetonitrile is there for you. It is a liquid, it has a boiling point, I think around 60 degrees, 60 or 70. So it evaporates pretty easily if you want to evaporate it off of sample. For me, I'm a photochemist, so it's important for me that acetonitrile does not absorb light, visible or UV light, all the way down to 200 nanometers, so deep into the UV. It mixes with water very well, and it's pretty cheap, pretty non-toxic. It's great at dissolving all kinds of different things. This guy's my favorite. Personally, I like to use acetonitrile. DMSO and DMF, the problem with those is they are very high boiling, so they're difficult to evaporate away. If you ever want to dry it, like if your sample has it contaminated in it, you can't just dry it off. Very easy. Acetone's a good one too, but I like acetonitrile better. All of these are what we call aprotic polar solvents. So keep in your mind 3 kinds of solvents. We have non-polar, polar protic, hydrogen bond, or polar aprotic, which can't hydrogen bond, or at least can't be hydrogen bond donors, but they're still polar molecules. Great. It turns out that polar protic solvents are really good at solvating ions. So if they can hydrogen bond, they stick like glue to ions in solution. That's why water is so good at dissolving salts, because salts can turn into ions, you know, Na plus, Cl minus, and the water molecules will stick to them, and they form what we call a solvent shell. Okay, and they stick to them, and that stabilizes those ions, stabilizes those charges, and makes those charges very stable as standalone ions in solution. Okay, so this solvation shell, if you're trying to do an SN2 reaction or an SN1 reaction in a polar protic solvent like water, and what happens is you have, typically, if you have a strong nucleophile, you have ions, water is going to form this coat around it. So it's not just a Cl minus or an OH minus or whatever in solution. It's that plus its entourage. It's got all these water molecules that are sticking around, forming this solvent shell, that when that ion moves through solution, it's dragging all of these solvent molecules around with it. It's not just freely swimming through. So it turns out that if you have nucleophiles in solution, polar protic solvents make those nucleophiles weaker. Imagine you're like running a race. Okay, you're the nucleophile in this story. You're running a race, but there's a whole bunch of toddlers that are like grabbing onto your legs as you're trying to run. I don't know why toddlers, but yeah. And imagine you could run and maybe you can still get through and you can fight them off and there's more coming on. And you can make it through, but it's going to slow you down. That's what the solvent molecules are like with nucleophiles. Negatively charged nucleophiles will get wrapped around in water molecules, and they have a hard time. It makes them weak. They're weakened or slowed down by all these polar protic solvent molecules. So it turns out, if you look at halides as nucleophiles, they can be leaving groups or nucleophiles. It turns out that fluoride is an awful nucleophile when it's in water. And the thing is, fluoride is small, charge is compact, it's in a small package, and water sticks to that like there's no tomorrow. So fluoride has an extremely strong solvent shell around it and has a very, very difficult time acting as a nucleophile because it can't shed that water. That water shell around it is so tight and so strong that it makes fluoride an awful nucleophile. In fact, biology, and when I talk about biology, I mean like, I guess, evolution, biological systems have not found an effective way to use fluoride to make organic molecules. It can use almost every other element. There's organic molecules that has a bunch of crazy elements, bromine, chlorine for sure, phosphorus, nitrogen, sulfur, selenium, a whole bunch of things. But fluoride, despite how abundant and common and small, all these things, fluoride is generally not found in naturally occurring organic molecules. That's because natural fluoride is typically in water, and in order for an enzyme to place fluoride in a molecule, it has to strip all those waters away, and that's just too hard. Biology has not found a way to do that yet. Effectively. Chloride suffers from the same problem to a lesser extent. And when you got all the way to iodide, iodide is big. So I guess now imagine you're running the same race, and instead of toddlers slowing you down, it's like, I don't know, ants, right? Iodide is huge compared to the waters. So iodide has no problem. It just pushes the waters out of the way. It goes and it attacks. Because it's big and the charge is spread out over much more volume, water doesn't hold iodide as tightly. So iodide actually is a really good nucleophile. And then as the halogen gets smaller and smaller, it gets weaker and weaker. Okay. So SN2 reactions, generally speaking, are slowed down by polar protic solvents. So if you want it to go SN2, don't pick a polar protic solvent. Don't pick water. Don't pick ethanol. Pick a polar aprotic solvent, like acetonitrile or acetone or DMSO or DMF. These are the best solvents for an SN2. If you do an SN2 in a polar aprotic solvent like DMSO, then what happens then? If that happens, the order of reactivity for those halogens flips. Fluoride becomes the best. If you get rid of those waters, and because we're smart human beings, we know how to get rid of those waters. Take sodium fluoride as a salt, dry, put it in DMSO with no water, you can just get fluoride ions, and we call them naked fluoride, because fluoride loves water so much, if you keep the water away, the fluoride behaves very differently. It behaves as if it's naked. It doesn't have that coat of water around it, and fluoride becomes the best nucleophile if you're in a polar aprotic solvent. That's because it's not surrounded by these toddlers slowing it down. I don't know why I went with toddlers. And it's small, and it's concentrated charge. That's actually great for a nucleophile, because it can get into small, tight spaces. Because we said that if it's, you have too much junk in the way, SN2 is really slow. Well, if the nucleophile is tiny, then it has an easier chance getting in. And then iodide is the worst in DMSO because it's biggest, basically. So the ordering of how good the nucleophile is flips when you go from a polar protic to a polar aprotic. Polar aprotic, in general, is best for SN2. Okay. Lots of text on these slides. Think about an SN1 reaction. SN1, rate determining step, looks like this. You're forming ions. So if you are doing a reaction where you're trying to form ions, a polar protic solvent is going to be your friend. Because polar protic solvents form shells around ions. That stabilizes those ions, makes them more stable. So if we're trying to make a carbocation, it's a lot easier to make it if you're in a polar protic solvent where the solvent is stabilizing those things that you're trying to make. So SN1 has sort of the opposite reliance on solvents as SN2. SN2 prefers polar aprotic, SN1 prefers polar protic. And that's a decision that is under your control. When you set this reaction up, you weigh things out and you mix them together, you choose what solvent you put in there and mix, right? So if you want it to go SN1, pick water, or pick ethanol, or pick something like that. If you don't want it to go SN1, pick one of those aprotic ones. It's a good way to think about it. All right, what else can you control? Well, you could pick different starting molecules with maybe different leaving groups. Turns out the best leaving group of the halogens is iodide. That's because out of all of the CX bonds, carbon iodide is the weakest. So iodide comes off most easily. You know why Ci is the weakest out of them all? We kind of talked about this back in the acid-base chapter a little bit. It's because iodide is huge. It sounded like Donald Trump when I said huge. Iodide is huge, carbon is small, very different sizes. Overlap of the orbitals is really bad. Bad orbital overlap means weak bonds. Use the same idea when we talked about why HI is a stronger acid than HCl. So yeah, as the iodide gets bigger, the bond gets weaker. And as the bond gets weaker, the leaving group comes off more easily. So fluoride actually is a terrible leaving group. Awful. In fact, you can't do SN2 reactions or SN1 reactions if you're trying to use fluoride as a leaving group. Because fluoride is the same size as carbon. And because it's the same size, it forms an amazingly strong bond. So this is actually a real problem because, I said biology hasn't figured out a way how to put fluorides on organic molecules. Well, human beings sure have figured out a way. In fact, around 50% of drugs, new drugs that are developed, have carbon fluoride bonds in them. Not only drugs, but like Teflon is full of carbon fluoride bonds. All kinds of products have carbon fluoride bonds. And these ultimately end up in the environment. And not only can biology not insert fluorides into organic compounds, they also can't remove them very effectively. So these compounds tend to be very persistent. They survive for a long time in the environment. And why can't biology take fluorides off very well? Because carbon fluoride bonds are super strong. SN1s and SN2s don't work to get rid of them. So in between, bromide and chloride are kind of intermediate. Iodide is the best leaving group, then bromide, then chloride. And we don't even call fluoride a leaving group because it doesn't leave. It stays around. It's an unwanted house guest. Well, sometimes you want it there. Other leaving groups that we will use, we may or may not get to chapter 11. We've got a lot of awesome leaving groups that we can talk about when we get to that chapter. But if we don't get there, water is a good leaving group. So how do you get water as a leaving group? If you have ROH2 plus, the heck is that? Well, I'll show you. If you have, let's say you have an alcohol, let's go something like this, OH, tertiary butanol. You can't just have hydroxide leave. Hydroxide is an awful leaving group. Strong bases, if something falls off and it's a strong base, it's going to be a really bad leaving group. So you can't just like kick off a methyl minus. You can't kick off a H minus, and you can't kick off a OH minus. But what you could do is react this with an acid like HCl, and I'm going to remove that arrow, and protonate, do a proton transfer first. Now you get something like this. Now we've got a great leaving group. We can pop off that. So water was our leaving group here. Water can only leave if you have an alcohol that you protonate first. So you need a strong acid in order to cause that kind of a reaction. So there are other leaving groups that we can take advantage of, or at least take something that's on your molecule and turn it into a good leaving group. Because hydroxide's awful as a leaving group, but you can make it a good leaving group by protonating it. So halogens, iodide, bromide, chloride are good leaving groups, or small neutral stable molecules like water make good leaving groups if you protonate the compound first. All right, so that's what strongly basic things are not. So you can't just do SN2s and knock off strongly basic molecules like H minus or CH3 minus, not leaving groups. All right, so summary between SN1 and SN2. Substrate is tertiary, it's definitely SN1. If the substrate is primary or methyl, it's definitely SN2. If it's secondary, it could be either SN1 or SN2 depending on the conditions. Stronger nucleophiles sway it towards SN2. Polar aprotic solvents sway it towards SN2. Polar protic solvents sway it towards SN1. Leaving group, actually, the leaving group falls off in the rate determining step for both SN1 and SN2. So a good leaving group speeds them both up. A bad leaving group slows them both down. Okay. So when would a good and bad leaving group even matter? Well, let's say you have a reaction where you have a molecule that looks like this. And you're going to do a reaction. We need a nucleophile like NABR. And we want it to go SN2, so we'll use a polar aprotic solvent like DMSO. So remember, anytime you see sodium anything in this course, dissociate them apart, and we have bromide. Plus somewhere else we have Na+. We have our substrate, we have our nucleophile, and we have two possible sites of attack, there versus there. Both are primary. It could attack one or it could attack the other. Which is it going to attack first? Which is the preferred place of attack? Prefers to go to the iodide and knock that out. This would be the preferred reaction here because iodide is a much better leaving group. It'll leave much more easily than the chloride, and so that's the one that'll be preferentially knocked off. So sometimes you have complex molecules with lots of potential leaving groups. The reaction will always knock off the one that is the weakest, or the best leaving group, the weakest bond. Cool. Now, We can use substitution reactions to make all kinds of different functional groups. You can use hydroxide as a nucleophile to make alcohols, alkoxides as nucleophiles to make ethers, SH minus to make thiols and thioethers. We didn't talk much about thiols and thioethers, but they're things. You can use cyanide ions to make nitriles. These guys we're going to talk about in more detail in a later chapter. They can make alkynes, make esters using carboxylates. You can use amines, and you can use azides. Azide is like the best nucleophile of all. So we can make a whole bunch of different kinds of functional groups from alkyl halides, which is great. So this is called sort of functional group transformation. We're changing one functional group into another by using substitution reactions. Now we're not done with this. It might seem like I gave you a few examples and then showed you there's a whole bunch of things that can happen and then we're leaving it behind. We're not leaving it behind. We're coming back to SN1 and SN2. There's more we got to kind of discuss before we do a more wholesome, full discussion of these things. Which is, now that SN1 and SN2 are starting to crystallize in your brains, I'm going to take a big wrench and throw it into everything and just say, wait, there's two more. Two more reactions in addition to SN1 and SN2 that can also happen for alkyl halides under this same set of conditions, which is probably the exact thing you don't want to hear. Trying to sort out between these two mechanisms, and I'm going to say no. You have to sort out between 4 mechanisms. There's 4 that can happen. The other reaction is called elimination. Luckily, the name again tells you what's happening. You're eliminating 2 molecules, 2 atoms from your molecule, or 2 parts. And it looks like this. If you have 2 carbons that are adjacent, each carbon will have an atom or a functional group or several atoms. You remove 1 from one carbon, 1 from the other carbon. Those come off, and then you have a double bond form between the 2 atoms. So what would an example be? Let's say you have something like Br. You have 2 hydrogens here, hydrogen, hydrogen. An elimination would look like this. So HBr was the part that we eliminated out of the molecule. We removed it, and we leave behind a carbon-carbon double bond. This, of course, makes alkenes. And we're dealing in this chapter mostly with alkyl halides. Alkyl halides, have a halogen. If it's not fluoride, it's a leaving group, potentially. So if you have a molecule like this, where we have an alpha carbon and a beta carbon, alpha is the one with the halogen attached, and X, so it could be iodide, bromide, chloride. And on the beta carbon, you have a hydrogen. What we're going to do is remove H, remove the leaving group, and leave behind a carbon-carbon double bond. Now this may seem, when you see reactions drawn like this, and it's all symbols and B's and R's and general X minus, it may be hard to sink your teeth into, but we will look at real molecules doing real things. So here's one. Here's an alkyl halide, 2-bromopropane. What kind of an alkyl halide is that? Primary, secondary, or tertiary? Or methyl? It's secondary, this one. How can you tell? The alpha carbon is the one that the leaving group is on. We have a beta here and a beta here. In bond line structure, that looks like this. It's a secondary alkyl halide. And we're going to put it in ethanol. C2H5OH is ethanol, which is a polar protic solvent. Good. And we're going to add this thing, C2H5ONA. The heck is that? Well, it's got a sodium. First thing you see sodium dissociated. So In your brain, this should be Na plus or that. It's the conjugate base of ethanol. So if you take ethanol and add a really strong base to it, you can deprotonate it and make this thing. It's called an alkoxide. It's a very strong base, but it's also a nucleophile. How do you know it's a nucleophile? Well, it's got a negative charge and it's got lone pairs. Isn't that what we said nucleophiles have? Yeah. So it's both. So from what you would know at this point in time, you would expect that molecule with its negative charge and lone pairs to behave as a nucleophile with an alkyl halide and do an SN2 and do a substitution. But what I'm saying is that if you do that in this example, warm it up to 55 degrees Celsius, you don't get that at all. You get an alkene form, sodium bromide, and ethanol comes back. We get something else happen here. Not substitution at all, even though we just spent a long time talking about substitution. Here's another example. What kind of alkyl halide is that one? Yeah, that's tertiary. That's alpha, beta, beta, beta. So this is tertiary. This will do the same thing. This does elimination. Elimination always makes alkenes, always makes double bonds. Makes that very high yield, 90%, and then a few other things as well. This one can't do SN2 anyway, though, can it? Why can't it do SN2? Yeah, it's tertiary, so it's bulky on the backside. Bulky on the backside. That was my nickname in high school. No, it wasn't. Just kidding. Yeah, it's too bulky, so SN2 can't happen because the nucleophile can't come in. Great. So where do we get these things anyway? These alkoxides that do apparently now something new, this elimination and not substitution. You start with an alcohol and you can dissolve it. You can dissolve sodium metal in it. And sodium metal will do a reaction to make your alkoxide plus hydrogen gas that bubbles away. And you're left with something that looks like this. It looks like an alcohol, except the hydrogen is replaced with Na+. So it turns it into these very strong bases and also nucleophiles. SN2 isn't very good anyway because we're using a protic solvent. Right? Ethanol is a protic solvent because it can hydrogen bond. And we said protic solvents, that's not great for SN2 because it slows down the nucleophiles, forms solvent shells around them. Great for SN1, but not for SN2. These alkoxides, so what you can do is you take your alcohol and you can put a little piece of sodium metal, or in this example, you can put potassium metal in there. Hydrogen will start to bubble. The metal will start to dissolve away, and you can make these alkoxides, which are great for doing these elimination reactions. You could use terp-butyl alcohol, which is this big thing over here on the left. Now that one right there, that terp-butyl group is big. Remember, every time you see terp-butyl in this course, think big, size, large. And you end up making an alkoxide that looks like this, which is huge. This, I said that alkoxides can be nucleophiles or bases. If it's really big, bulky like this, it actually makes for an awful nucleophile. Because nucleophiles have to come in and attack, come close to the carbon, push the back methyls or whatever is there out of the way, come in and form an oxygen-carbon bond. That's difficult for it to do if it's got all this baggage coming with it. So this particular alkoxide is a bad, let's say terrible, terrible nucleophile. But it's a fantastic base. So this means this nucleophile slash base is bad for SN1 or SN2, but it's great for these elimination reactions. Another way you could do this is if you don't want to use sodium metal or potassium metal, or you don't have it, you can use sodium hydride. That'll do the same reaction. That'll also make alkoxides. Well, alkoxides are pretty easy to make. Right? You just take your solvent, chuck in a little piece of metal or metal hydride, and you can get your alkoxide that way. All right, we are out of time. I'm almost done blowing your mind. And once I'm done blowing your mind, I'm going to bring it all back together. Okay? I'm going to show you an easy way to determine when you have a specific set of conditions, how to predict what the right mechanism is going to be for that set of conditions. Okay? And that's really the whole goal of this chapter, is to be able to look at a reaction, set of conditions, and predict what's going to happen. All right, have a great 2 days, and I'll see most of you on Friday.